Okay, so we are continuing our march through chapter 2 and into chapter 3. In this video, I'm going to work to try to explain what the canonical distribution and the partition functions happen to be. These are big words that don't have a lot of physical meaning to you yet, but hopefully I can change that by the end of this video. Okay, so energy. We keep talking about energy. And at one point, we said that we can understand our system if we say that all extensive variables are constant. And then we said, well, energy is an extensive variable, so we're going to make that constant. Well, and then in our definition of temperature, we said, okay, the total energy is constant, but we'll let our energy of our system change as long as the energy of the reservoir also changes. And this is somewhat, and that means that we're kind of trying to make it both ways with energy. If we want to set energy as absolutely constant, we assume that the system, and so our energy of our system isn't absolutely constant, assumes that the system is going to be completely isolated from the surroundings and energy cannot transfer. This is impossible. So, what if instead of controlling the energy of the system and the surroundings, what if we control the temperature? Because we learned in our last video that temperature is defined as the derivative of energy with respect to the entropy, holding the number of moles and the volume constant. And so one way of controlling the energy is by maintaining the temperature. So we're going to work on this. So the canonical ensemble is a system in which we define that the temperature, the volume, and the number of moles are constant. These are all three variables that we can control. The temperature we can control by putting it in a constant temperature environment, a water bath, the room, anything like this. The volume, if we have a sealed container that's rigid, the volume stays constant. And the number of moles, if we have a sealed container, what we put into that container stays in that container. So these are three variables that experimentally are controllable. But now that we've redefined our system, we have to redefine this probability of a particular microstate. And so what we are going to start with is we're going to start with our definition of temperature. And in grad school, I would say it can be shown that, which was, in my program at least, was code for your homework is going to expect you to do this. But we're not in grad school yet. So I'm going to ask you just to believe me that with some algebra, we can convert our definition of temperature to this equation in terms of microstates. So we're using our same notation here of the omega of the reservoir as a function of the energy of the reservoir is equal to the microstates of the reservoir as a function of the total energy times E raised to this energy exponential, this E divided by kBT. And remember that these two equations are identical. They're just rearrangements and redefinitions of the same thing. Okay, so starting from our rearranged definition of temperature, the probability of the system existing in a single microstate is given by this fraction. So I have the microstates of the reservoir divided by the total times this exponential function of the particular energy. So we need to get rid of this issue of having microstates in our formulas because we've covered thoroughly that microstates are really hard. So to do this, we are going to normalize this probability distribution. That means that if we took the integral of the full function or we added up all of the possible probabilities, that everything should be equal to 1. And so we do this mathematically. We find out how to normalize this. And so that means that this pi function that we've been working with, this is now a fraction of the microstates that are demonstrated by the system. Okay, so if we rearrange this expression that we've set equal to 1, we find that this fraction of the microstates is equal to 1 divided by this weird summation. Well, if you haven't figured this out yet, the pChemist trick is when we have a really funky function that we don't like to write a lot, we give it a variable name. And so this funky function that we don't like to write a lot, we call Q of t. And so our probability distribution can now be rewritten as this exponential of this single energy state divided by Q of t, which is our total. So this becomes a part divided by a whole or a fraction. So you're probably going to be thinking, this function on the bottom, this looks really complicated. It's got a summation up to infinity of this exponential term. This looks really hard for us to deal with. And it turns out that it sort of is, but we're going to kind of walk through the different types of conditions and the different types of energies that can exist so that we can understand what this Q of t is for different components of our system rather than thinking of our system all at once. Okay, so we started all of this off with a discussion of temperature. And remember that temperature determines how likely the system is to be found at any particular energy. And so what does this mean? Notice that we've got temperature both in the numerator and in the denominator. And what happens is that if we have, so KB times T is an energy unit. So if we say that our temperature times the Boltzmann distribution is equal to twice our energy of our ground state, then our molecules in our system can really occupy the first 4 energy levels, with the majority of these molecules being in the ground state. So these are really our electronic energy levels in this example, and we're just using these as an example case. If we say now our temperature is 5 times our ground state energy, notice that we can start populating eight levels. And see how now things are much less distributed? We have many fewer molecules in our ground energy state. And likewise, if we have increased our temperature so that it is now equal to 8 times our initial energy, now all of the energy levels that we've considered, all 11 levels, I can count, have the possibility to be populated. And notice that at this point, there's nothing special about the population of that ground state. So as we increase the temperature, as we add energy into the system, the possible microstates that exist change, which that made sense based upon our definition of temperature that we created. Remember that temperature is defined as the partial of the energy with respect to entropy. And so when we start combining these microstates and this probability and temperature, we should always keep in mind that temperature is really determining how many of these energy levels can fill. Okay, so before we had defined our probability as P of I. We were thinking about what is the probability of a particular microstate existing. We've covered that microstates are hard, impossible even. And so we don't want P of I. Instead, what we would really like is to be able to find the probability of an energy existing, because energy is something that we can define, we can measure, and we can understand. And so it turns out that with some math, we can go from PI to PE, because we know that energy and microstates are linked by temperature. And so if we do that, we get this new expression for the probability of a particular energy. Now, note that this is the total energy of a microstate, of a system. It's not the fraction of microstates with a... So it's not one molecule with a particular energy distribution, or considering a set of molecules with a particular energy distribution. Instead, it's thinking about a fraction of the microstates, so the conditions of the entire system with a given energy. And it doesn't matter what contributions to the system that these different molecules are making. As long as the system has the same energy, it's going to be factored in. Okay, so we keep moving back and forth between talking about molecules, and then we talk about a system, and then we go back to a molecule. So the probability of a molecule existing within a particular energy or a specific quantum state is given by this probability. Notice that this E. We've switched to this epsilon. This is energy, but this is energy for a molecule. We will use the capital E to indicate the energy for the system, that more total energy. And notice how we have Q of T here. We use capital Q of T for the system. This is going to be for the molecule level. And Q of T is going to be defined in a very similar form as what we had before. But this time we have, before we had this omega of E times e to the minus ei over kBt. Now we have this weird g of epsilon times the same energy function. We're going to talk through that. So this g of epsilon is known as the degeneracy. It's going to be a count of the number of energy levels with the same energy. So in the probability distribution, it's going to scale the expectation of that state based upon how many possibilities exist for that state. And for each different type of molecular energy that we consider, we're going to think about what the degeneracy it can be for that system or for that condition. Okay, so you're now try this. At 298 Kelvin, room temperature, calculate the ratio of the number of ammonia molecules in the excited state as compared to the number in the ground state. The energy of the excited state is going to be 932.43 centimeters negative 1 above the ground state, and the Boltzmann constant in useful energy units is given to you. Now, we're going to go into this a bit more in depth in a couple of videos, but this is called wave numbers. You've seen this before. You used this in FTIR in organic lab. Wave numbers is a unit of energy. It's a very odd unit of energy, but it's a very convenient unit of energy because it turns out that wave numbers, which I'm going to, for now, give the term nu bar. This is wave numbers. Times Planck's constant times the speed of light gives me energy in units of joules. And you should be able to play with the units to prove this to yourself. And so since HC are constants, we consider that wave numbers are proportional to energy, and so spectroscopists are lazy, and so we say that wave numbers are a unit of energy. It just means that the Boltzmann constant then needs to be in units of wave numbers.